Welcome to this lecture on network analysis. If you remember, in the last class we derived this equation for the current I, and we said that I is equal to e to the power minus pt integral q e to the power pt dt plus k e to the power minus pt. Now, in certain cases when the factors q and p are constants, the equation or this integral gets simplified, and the equation for current is reduced to this equation, where I is k1 plus k2 times e to the power minus t by t, where the term capital T is the time constant. Now if you take a look at this equation, it's easy to see that this k1 term is independent of time. So this is known as the steady state component. I'll write here k1 is the steady state component, and k2 is the transient k2 e to the power minus t by t is the transient component. Now if we have to calculate this parameter k2, we will take a look at the time t equal to 0, and we say that I0 is actually k1 plus k2. So k2 we can find out using this equation, that is I0 minus I of infinity. Now if you take if you put the values of k1 and k2 in the above equation, that is the equation for I, the equation for I can be written as, I'll write it down here again. The equation for I will be I infinity plus I naught minus I infinity times e to the power minus t by t. So this is the equation for current when the factors p and q are constants. Now to understand this, let's take a look at this circuit drawn in black here. We have a voltage source V, an inductor L, resistors R1 and R2 connected in this arrangement. Now what is done in this case? The switch is initially off. And when I say the switch is off, we mean that the switch is not connected. So in that case, what happens? The current follows this path. It is easy to show that the current follows this path. And since this inductor behaves as a DC, when the circuit is connected like this for a very long time, so what can we say? That the current before the circuit was closed, or current before the switch was closed rather, the current has the value V divided by R1 plus R2, because inductor will behave as a short, and only R1 and R2 will be the two resistors connected in the circuit. Now we also recall from our earlier studies that in case of an inductor, the current does not change instantaneously, or in other words we can say that current before switching is equal to the current after switching if the time instant is very small. So if this is the current before switching, this is the switching instant. If the switching instant is very small, this is current before and current after. If this is a very small interval, the current before and after switching will remain the same. So then we can make this we can write the equation that I naught, which is the current at time t equal to 0, current at time t equal to 0 is equal to I naught is equal to V naught divided by R1 plus R2. So t is equal to 0 is that time at which the switching takes place. Okay, so when the switching happens, what happens to the circuit? If you look at this diagram now, let me remove this orange mark here so that you understand clearly. So when the switch has been turned on, okay, so what happens? This R2 resistance is actually has a short in parallel to it. So what will happen to the path of the current? The current will follow this path. It will not go through R2, but it will go through R1 only. So we can say that the current I infinity, or the current in steady state, when the switch is connected for a very long time, the current takes the value V divided by R1. Now, these two values are known to us. If you take a look at this equation, the I infinity is known to us, I0 is known to us. What is left for us to find is this time constant T, right? So in an RL circuit, like the circuit shown in this figure, this is an RL circuit. The time constant of this circuit after the switching has been performed, is equal to L divided by R1. Now if you ask where this time constant comes from, this time constant simply comes when you formulate the differential equation. Time constant, formulate the differential equation. And from this differential equation, you will find out you will be able to find out this time constant. Now, when you know the I infinity, I0, and all of these terms, and the time constant, you can then simply say that the current in the circuit I takes on this value, which is I is equal to V divided by R1 minus R2 divided by R1 plus R2 times e to the power minus R1 T by L. This is the expression for the current in this circuit. Okay. Now, if you take a look at this graph, let me redraw this graph for you to make you understand. This value is I infinity, or the steady state value of the current, which is given by I infinity is given by V divided by R1. Another value which we have with us is I0, or the initial value, that is equal to V divided by R1 plus R2. So you can clearly see that I0, the value I0 is less than the value I infinity. So this is the value. I0. The graph here shows that this is the same current which was present before the circuit. Now if you were to calculate the total current, it will take this form. It will take this form like this. It will be an increasing graph like this, such that the total value of the current is I is equal to V divided by R1 1 minus R2 divided by R1 plus R2 e to the power minus R1 by L times T. So this will be the blue curve. This will be the graph of the current through this circuit. Fine. This is one example. Now let's take a look at the same circuit, but with slightly different conditions. The different condition here is that we have the same circuit as was before with us, but instead of closing the switch at t equal to 0, we open the switch at t equal to 0. So what does that mean? That means that before t equal to 0, before the switching, the circuit was connected like this. Okay, so the direction of current would be like this. No current would go through R2. All of the current would go through R1 only. In that case, what is the value of the initial current I0? It is V divided by R1. And what about the value I infinity? This is V divided by R1 plus R2, because when you open the switch at t equal to 0, what are you basically changing? The current in the circuit will follow this path now. So this resistor R2 is now coming into the circuit. So I infinity is the current after the switching. Current after switching. Okay. Also, in the previous case, we calculated the time constant. What will be the time constant? It is the calculated from the differential equation after the switching has been done. So if you formulate the differential equation for this circuit, you can easily find out that the time constant t is equal to L divided by R1 plus R2. Okay. So if you take a closer look at I naught and I infinity, you will clearly see that it's the reverse of the previous case, or it's the reverse of the previous condition when the switch was closed at t equal to 0. Now if you substitute all of these values back, into this equation I, you will end up with this relationship: I is equal to V divided by R1 plus R2 times 1 plus R2 by R1 e to the power minus R1 plus R2 t by L. So this is the term that you will end up with, and this is the expression for current I through the circuit. All right. So with this we come to the end of this section, that is the calculation of the currents. Now what I want you to do on your own is that you draw the waveform for the I0 and I infinity and find out the waveform for the current I in this circuit. Okay, it will be you can take help of this waveform which we have discussed, and you find out the waveform for this particular equation. Also, I want you to read and solve some more problems which are given in section 4.4 of the book. There are two solved examples, example 3 and 4 in the book. You please go through these examples, solve them on your own, and try to understand what is happening. And at the end of the chapter, in the book, there are some unsolved problems. I want you to solve problems 4.1 to 4.6. So these are 6 problems in total. I want you to solve them on your own. And in the next class, which will be on Tuesday, I'll be randomly asking students about their this assignment, and only those students will be given marks who would have done these 6 problems. Okay, so make sure you finish reading all of the things that have been assigned to you, and you do all of these problems on your own. You read the book, you can refer to the book if you face any doubts, and if you have any questions about this, that will be I'll address them in the next class. So you have time till the next class. You please complete all of these assignments, and then I'll see you on Tuesday now. Thank you.